start, Camilo?
Yeah.
Here I have Camilo, who is Dr. Arnold. Who's from Dr. Arnold's group. I mean, I should say who was from Dr. Arnold's group. He graduated, I think, in 2018, right, Camilo?
2017.
2017. Yeah, I had come in 2016, so he graduated a year later to me. And Camilo is awesome. He's taught a lot of us, like he's taught COMSOL to a lot of us. And in that time, very few people were using COMSOL. So they were very lucky, or should say very chosen, a few people who actually got to learn from him. So this is actually a nice time for a lot of people to learn from you. And Camilo is now doing his postdoc at CMU. And Camilo, if you want to say anything about your postdoc, if not, then I guess we should just start with the workshop.
Yeah, thank you very much, Kartik, for the introduction, and happy to be back and try to share the knowledge. The model that we have chose with Kartik, it's gonna be a Joule heating actuator, and we are using this one because at the postdoc at Carnegie Mellon, we are working in a micro-robotics program. This is a program with DARPA, with the Department of Defense, to try to make small robots 10 millimeter by 10 millimeter by 10 millimeter in size. That's the maximum. And we precisely need this type of actuators to make the robot do things. So I think it's going to be very useful, and at the same time, it's one of the first MEMS devices, MEMS actuators. But still, there are a lot of things to do there, and they are very versatile. So hopefully, everybody enjoyed. And Kartik mentioned, please be aware that we're going to record these sessions, so as we can post it after in the wiki, in the IMG wiki. So if everybody has any trouble, let us know, and we can stop recording. There is no problem with that. So let's jump in. So let's start. Well, we're going to assume that people knows a little bit about COMSOL, and people has doing some things. So what we're trying to do is model a Joule heating. I'm going to explain what is that for a unimorph actuator using COMSOL Multiphysics. I'm going to start from scratch, but please feel free to interrupt or ask questions at any moment. What I'm going to try to cover is some of the geometry and the materials definition. Of course, after explaining what is this unimorph actuator, and we're going to use some physics, the electric currents, the heat transfer in solids, the solid mechanics, and one that combines the three of them, that is kind of the multiphysics model for COMSOL. At this point, perhaps you're aware that COMSOL Multiphysics, it's a program that allows us to do multiphysics simulation. It means it's trying to solve the differential equation, the partial differential equations for multiple physics by using the finite element model. So it's basically divided the problem in tiny squares or triangles and trying to solve local for a domain, and it tried to impose boundary conditions and try to solve for the next domain, and so on, and so forth. We're gonna see the three main components of the studies. It's gonna be, of course, a mesh definition. We need a stationary study, a parametric sweep, and a time-dependent study. So hopefully we're gonna have time to present everything. This model, it's really very simple, but if we are careful, we are gonna understand this. So let's start in what is a unimorph actuator. So basically it's a cantilever that has two materials. One of them is an active layer that it could be a piece of metal that heats, it could be a piezoelectric, it could be a shape memory alloy. Those are examples of pictures of our research at CMU. Those are made of shape memory alloys, and we are using basically the same model that I'm going to present today. It's just there is a hysteresis in the shape transition that we consider, but we are not going to talk about that one. And after the active layer, there is a passive layer that could be a polymer, an oxide that is helping just curve these things up and down. I need to thank especially to Dr. Manoush Babey. She's a postdoc at Carnegie Mellon as well, and she has been developing most of these shape memory alloys and the model that we're using today. So as I mentioned before, we have two layers. It's in a simple beam, it's gonna look like this. One is passive, one is active, and whenever we hit one of this, like you're seeing here, the temperature is gonna start deforming both materials, but because of the thermal mismatch on the materials, it's gonna start curling down in this case, or depending on the geometry, it's gonna curl up. But for this one, it's the thermal coefficient or the thermal expansion for the passive layer is higher, so it's gonna try to bend forward. And the mechanism that we are going to use today, it's gonna be Joule heating. It means we have a metal, this active layer is a metal, we're gonna use nickel. We are going to pass a current through it, and the current is going to increase the temperature on the conductor, and we are gonna analyze what is happening in this region, and the change in temperature is gonna cause the transformation and the bending. So it's a bimetal or bilayer problem, and we just changing the temperature by heating. So let's start. The geometry is going to be very simple. It's a U shape, basic, and it has 15 micrometers wide, and it's gonna be 105 micrometers long. The thickness of the metal layer is gonna be nickel, and it's gonna be 1 micron, and the thickness of the IPS is 15 microns. All the dimensions that I present today, they have been validated. Even they haven't been validated for nickel specifically, has been validated for nickel titanium. That is very close at some point to this model. So we know that the problem works in this regime. And the last thing that we need to include is a box for the air. I'm gonna explain why do we need this box of the air, but just imagine encapsulating everything in air. So let me jump into COMSOL at this point. I'm gonna jump back and forth between COMSOL and the presentation. And for the ones who are not very familiar with this, we work here in the model builder, and basically, and you have some global definitions. There are some parameters. For example, at this moment, we are selecting a current that we call initial current, and it's 15 milliamps. That's the only parameter that we're gonna do. And then we have a big component, and this big component is gonna be one single simulation, one nice piece of simulation. Inside this component, we have the geometry, and I have been working in one work plane. Let me delete this. So basically, in this work plane, I've been drawing these shapes. The first drawing is this box that is 15 micrometers by 105 micrometers long. I just right-click on plane and add a rectangle. And when I add this rectangle, I select the width and the height. And I move this to make it in the center, so I move it to 7.5 micrometers in wide. I repeat the same for this other rectangle, and you will see that this is 15 microns by 105, and I shifted this corner to 22.5 micrometers. It's very important that at the beginning you select in geometry here the length unit instead of meters, micrometers. Otherwise, the results are going to be completely crazy. So micrometers, we have the 15 microns and 105, and we are missing one component, and it's the top. I'm adding another rectangle that is 45 micrometers long, and this is 15 micrometers wide. And I'm gonna put it at minus 22.5 microns, and I'm gonna move it to the front 90 micrometers. And if I build the selected, now we have this nice shape. For simplicity, because all these represents the same material, I like to use a Boolean transformation and give the union and say, please do not keep the interior boundary. So I want to remove these boundaries here. So I build the selected, sorry, I need to select the three materials, and I build the selected, and now I have a nice layer. This is gonna be the fundamental layer for the active and the the active and the passive. So let's go for the active layer. So we are at this point we only have this, we have just a layer. I'm gonna right click here and I'm gonna set this plane here in the work plane. I'm here in the work plane and I hit right click and please extrude this material. I already deleted, sorry. I had it for the example, but I wanna do it with everybody. So here in the work plane, I right click and I say, please extrude, and I'm gonna extrude this area. You notice? I'm selecting this one. And I said, please select 15 micrometers and build the selected. Okay, so now I have a nice construction and this is the passive layer. What I'm gonna do is I'm gonna duplicate this. Well, let's get rid of the block. The big block is this one here, and I just right click on the geometry and add a block. And I have a nice block of 90 microns, 120, 90 microns here in X, 120 in Y. It's very important to understand that this is the Y, look, this is the Y, the X, and the Z. And for the height, it's gonna be 50 microns. But I want this right in this edge, look, right in that edge, and touching these materials. So I move it minus 45 microns in X to be in the center, 0 in Y, and minus 17 in Z, just to be here at the center. So right now I built all the objects. Sorry, I built all the objects and I have that. And the last thing that I need to do is define, I'm gonna duplicate this one, the same work plane, to define the active material. So I'm gonna duplicate, it's the same geometry, no need to draw it again. And I'm going to right click and say like extrude, but instead of going 15 microns upward, I'm going minus 1 micron down. So right now it looks like this, where you can see 1 micron of active layer and 15 microns of the passive layer. People will ask me why the difference between 1 micron and 15. Well, we have discovered that for the different coefficients, this one is the thickness that will maximize the work at the end. I mean, the force dense displacement product at the end. So that's why we choose that one after long characterizations and things that I'm not gonna present here. The next thing is assigning the material. So I already have preloaded 2 materials. One is called IPS, and I add some thermal values that we found in the literature, the thermal conductivity, the density. Sorry, I forgot to mention the IPS is a polymer, and this polymer we use it as a passive layer because we can 3D print it, that polymer on top of the metal. The metal is going to be microfabricated. It's going to be a spotter on top of a silicon wafer. We're going to pattern that one, and then we're going to 3D print the polymer on top. We are using a 3D printed that has a resolution in the like 200 nanometers that is called nanoscribe. And the polymer that we use with them is IPS. So the literature, the vendor offers a lot of the values here for thermal conductivity, density, heat capacity, coefficient of thermal expansion. This is the most important one, 52 times to the minus 6. Meanwhile, the nickel, it's the coefficient of thermal expansion is 7.6 times to the minus 6. So there's clearly a mismatch on this thermal coefficient of thermal expansion. I need to assign, yeah, I see that somebody's having a question. Let me see. Yeah. Yes, we have 2-photon polymerization and we have the nanoscribe, and that's what we are using for this one. So welcome to help everybody that is in the need of one of those. And we are using this for fast prototyping and try to understand better the actuator before we fabricate it at mass production. So for this one, we need to assign a models, a domain. So right now you can use the scroll wheel of your, oh, what happened here? Sorry. You can use the scroll wheel on your mouse to select different volumes. So I'm gonna right click on this one, I select the other one and right click. Now I only selecting for the nickel, the conductive part, and for the IPS, it's going to be the other part, that is the polymer. I'm gonna add another material, and this is a conventional, a library from COMSOL. So I right click and add materials from library, and I'm gonna use air. And I'm gonna select this material here. Okay, so I have defined all the materials and to all the blocks that I already fabricated. At this point, it's safe to save this value just in case, and we can continue with the presentation. Any questions so far? Okay. So those are the geometries, we define it. Those are the dimensions. I'm gonna provide this presentation in case if you want them. And those are the material conditions. We find this on the literature. And this is very important. Look, for the people who's new in COMSOL, the most important work in COMSOL is validation, okay? And the validation starts from the material properties. We have spent on these modules perhaps 1.5 years just tweaking the simulation, and there is one postdoc completely dedicated to this one. I'm not trying to discourage anybody. No, this is easy to pick up. The steep curve of learning for COMSOL is going to be like a couple of months, and you can start doing amazing things. But it's not enough just to have a model. You just need to validate it. You need to find out, for example, for your specific material, what is the thermal conductivity? Let's create an experiment to measure this thermal conductivity, because perhaps it's not the same that we have evaluated or we find in papers or in books. Perhaps our material is completely different and the Joule modulus is different, so we need to measure it. So validation on every single step is crucial in COMSOL. It's the most important part. So let's jump into the physics. Okay, and once you understand the variables, it's very important for you to understand as well that as any software, you can, the software is trash input, trash output. It means if you use as an input trash and a data, for example, a value that you haven't tested or an equation that you are not very sure, the result is going to be crap, to be honest. So don't expect the software. This is a very complicated software that is trying to solve very complicated partial differential equations, and you need to own the physics. You as a researcher needs to really understand what is happening at the fundamental level. So the smaller, simpler, and fundamental and more fundamental that you get, the better results that you're gonna get. So the first module that we're gonna try to talk about is electric currents. This is part of the AC/DC module, and it helps us to find or compute electric fields, current, and potentials. The thing is that they are trying to solve the current conservation equation based on the Ohm's law, the generic differential equation. So that generic differential equation is this one here in the bottom. Like the electric field is equal to the gradient of the electric potential. The thing is, there are other constitutive equations that we use, but it depends on the boundary conditions that we apply. So that's why this J term appears here, because it's different if we're using this in electrostatic, or if we're using an AC, or if we are using a magnetic field surrounding. So the equation, this equation and these equations are gonna change depending on the boundary condition. But the one that is not changing is this one here, okay? And you need to understand that fundamental is the equation. What is the equation that you are trying to solve, and what are the parameters that you are trying to solve? In this case of AC AC/DC, the conditions are simple. We are only gonna pass current in the active layer. Everything else is isolated. We don't care about that one. And the two boundary conditions are ground. We're gonna find that this area here, this is just a top view of the U shape. This part here is grounded, and the other part here is a current input. And in COMSOL, the inputs are called terminals, and this terminal is gonna have current flowing in this direction. So how do we see this? Well, first of all, we need to add a physics. And look, my biggest suggestion is don't try to make a model for yourself. COMSOL has a lot of multiple models that interlink to each other, and they are already tested and they already solve a bunch of problems. So try to use those. Try to use the help of COMSOL. In this case, we are going to add the physics. I'm gonna add a new physics that is in structural mechanics, and instead of structural mechanics, it's called Joule heating and thermal expansion. So it seems like one model, but in reality, it's combining three. So if I double click this, you're gonna see immediately that he already populated the system with four modules, like heat transfer, solid mechanics, and electric currents. Let's start with the electric currents because it's the first one that I mentioned. First of all, we are not gonna solve it in the air. We are not gonna solve it in the passive layer. We are only gonna solve it in the active layer. And give me 1 second to open the model here. Yeah, sorry about that. So for the electric currents, we only care about this one. We are going to have a discretization that is quadratic. This is just for the solution. The current conservation, we are not going to touch this part. The only thing is that we need to change this from non-solid to solid, because this part is solid, it's not air. We're not trying to solve the equations on air. We're just trying to solve the equations on a known material, okay? So that's very important. The second part, electric insulation, we are not going to change that. The initial value, this is pre-solved for COMSOL. We don't need to change it. What we need to change is add the two models that I mentioned before, ground and terminal. How do we add that one? So we right-click on electrical currents, and we said here, on a boundary, okay? You have three types of conditions. First, a volumetric condition, then a surface or a boundary condition, and third, you have a point condition, okay? So you can select those three types in COMSOL, and you can select the conditions. Depending on the conditions, you're gonna modify the equation. What equation? Again, if you go here, electrical current equation, here is the equation that we are trying to solve. Remember, I mentioned before, the electric field. So if we add more of these boundary conditions, this equation is going to start changing, and we are going to start adding factors. Okay, so right now we are going to say, please give me a ground. I need to select the ground. How do you zoom? You usually use the scroll wheel, and you click with the wheel and just move up and down, and you can, oh, sorry. You click the wheel and move up and down, and that's how you, let me close this so we're gonna have a better closed loop. Up and down, and you're gonna zoom, and if I move the other wheel, the right click and move, I'm gonna pan this, and if I move the right click, I'm gonna just displace, rotate this freely. This one is zoom out, and this one is go to the original view. So quickly, I'm gonna select this boundary as my ground, and I'm gonna select the other boundary as my terminal. So I go here, and I say, please use a terminal, and this terminal is going to be this one here, and this terminal is a current that we have defined here in parameters as initial input. So right now, go to terminal, and I say initial input. If everything is correct, if initial input was well defined in milliamps, this terminal here is gonna be in black. If you define this, I don't know, in volts, you made a mistake. Let's say that you make a mistake here. The terminal is going to be in orange here, and it's because you have a problem defining this variable here. So that's a pretty useful information. So right now we finish with this. I'm gonna take this moment to mention very important things here. Look, I know that sometimes COMSOL can be a little frustrating because it has a lot of information, but you need to seek help in the software all the time. And the best way to do it is right wherever you find a specific topic that you don't know, you go here to help and you click here in help or F1. And if, for example, you don't know which parameters to use in the terminal, wherever you are seated, the help button is gonna immediately open a window here and it's gonna tell you, hey, look, for terminal, we mean this. Look, the terminal is a node that provides boundary and domain conditions. And the options that you have for this terminal are power, are voltage, and circuit. So I can change voltage, current, circuit, or terminated, or power. Okay, so this is the best source of information. If I go to electric currents, look, in electric currents is gonna give me all the information, all the different buttons that I can select here are explained here. So this is very, very useful piece of information. Please use it. I'm going to go back to the presentation. We define the AC/DC. Now let's move to the heat transfer in solids. What is the heat transfer doing? It's trying to define the temperature equation in different solid domains using the differential form of the Fourier's law. Okay, the Fourier's law is only this portion here, that is the local heat flux. It's equal to the material's conductivity dot the temperature gradient. This is the only thing that you're gonna solve. The thing is, some materials behave with a different K. For example, some materials are gonna be capacitive depending on the heat. They're gonna have heat capacity depending on the configuration. You're gonna have some losses. You're gonna have some behavior that we are gonna add in this differential equation. More conditions, the more boundary conditions that we just select. But the overall equation is this one here, okay? For our specific model, first, this is a cross section of the unimorph. We have clamped this edge, and this portion of the edge, it's a temperature of 20 Celsius degrees. We need to define a room temperature in any place of the system. Otherwise, it's going to be crazy and he won't be able to compute the solution. So this is a boundary condition, room temperature, this edge here of the beam. And the second is, because we define an air, we are going to have a convection of the air, okay? And right now our air is a fluid, so we are gonna have a convection in fluids for the solution of this problem. The model always is going to try to do the conduction for the solid materials. So we don't need to care about this conduction. We just need to care about this convection. And it changes depending on your problems. Yes, if you have some trouble watching this message, we're recording this and we are gonna publish this information in the website after we finish. So everybody, if you need to leave or you have some trouble hearing, please watch the video afterwards. Just for a private comment that they made it in the presentation. So let's go again. We are doing convection in fluids and we are doing room temperature for this edge here. So if we go back to the model and we hit the heat transfer. So we have the heat transfer It's very important that our discretization is going to be a quadratic Lagrange. This is going to, for this particular model, is going to help us solving the situation, and it's just because the change in temperature, it's not going to be linear all the time, and that's why we don't want to have just 2 points from the beginning and the end and just making a straight line. It is going to change in a non-linear way. So that's why we select quadratic for this specific problem. We have the solid. We are not going to change anything on this one. And we have the initial conditions and the thermal. But what we are going to add is a boundary condition that sets temperature. And the temperature that we're going to set is for this boundary, this boundary, this boundary, and this boundary. Oh, sorry, and this boundary. These are connected to the silicon wafer, and the cantilever is going to be in the air at some point. So this is connected to the room temperature, and the rest of the beam is dangling on the air. So we need to use a different model for that. Very important, look, because this is a very common mistake. On top of each physics, you need to be careful on selecting the domains that you are using. Remember, here we are using electrical domain, but in heat transfer, we are going to use absolutely everything, including the air, okay? So be sure to link it, otherwise you're going to have trouble solving the equation. So boundary condition, the temperature, and the other one is convection in fluid because we have air. So right click, and you're going to hit here volumetric condition, and it's fluid. That's the volume that we are going to have. And we are going to select, because I deselect this one. Okay, I have fluid here. Don't pay attention to this Young modulus and Poisson ratio. I'm going to remove it in a couple of in a couple of steps. But here in fluid, I need to describe the fluid that I'm taking. But not only not only this fluid, but I need to select absolutely everything. I need to select not everything, but just the fluid, The other things have been defined already. And for this one, what we are going to do is, instead of being a gas liquid, it's a moist air because it's ambient air. So this is the most closely related to just common atmosphere under no vacuum. So right now we have fully defined the heat transfer. So if we go back, the next step is going to be the solid mechanics. The solid mechanics belong to structural mechanics, and it's trying to do the simulation of 3D and 2D bodies. And it has many equations, many fundamental equations inside. It's going to try to define displacement, stresses, and strain. And it's, I would say that is one of the most common modules in COMSOL. I mean, almost every module considers this structural mechanics. So the only thing, we're not going to be able to see the equations except if we select a specific boundary conditions. The only boundary condition, everything is going to be free. The only boundary condition is that this is a fixed constraint. Everything is going to move freely. And that's the only thing that we're going to do. Solid mechanics, the only thing in solid mechanics is that we are not going to simulate the air. We're going to remove the air, and we only care about the beam. Okay? The air is just for the heat transfer. So because we just care about the beam, we can remove it here, the air, and select the rest of the model. One important thing here, linear elasticity. This is already common for COMSOL. Depending on the problem, you will like to do you will need to change this one, but for this case, we don't need to touch it at all. And finally, we are going to add the simple condition that is a boundary condition. And we said like this is a fixed constraint. And we need to define the fixed constraint for this one, this one, this one, and this one. Okay, perfect. If we look carefully, the multiphysics are the combination of all these three. And we are saying like, oh, please, first, we are gonna have a thermal expansion. And this thermal expansion is coupling heat transfer with solid mechanics. Internally, he's doing it, okay? But if you go, sorry, internally it's going, if you can find the equations and try to see what is that. But the important thing is that they have been selected for you. You don't need to change this at this moment. Only I really suggest you to start changing these parameters if you are very confident with your physics and you are very confident with your the information that you have for the model. Otherwise, try to follow the COMSOL advice. Okay. Some important thing here is try to use the mechanical losses just to have more accuracy on the domain. We have the temperature coupling, and it's heat transfer and solid mechanics. That makes sense. And we have the electromagnetic heating, that is electric currents and heat transfer. But I'm not doing anything else. After that, I'm gonna select the mesh and I'm gonna build all.
Camilo, sorry to interrupt you. I think someone has a question, so I just thought, like,
yes,
if you can. Sorry. In the chat.
No, I'm not be able to. Can you read the question?
Yeah, so the question is, won't the surface contact between nickel and IP-S would also need a boundary condition?
Yes, you can create a boundary condition for that one, but for this specific problem, it's just a heat, as I mentioned here, it's just a conduction material. And when you use conduction material and you find heat transfer, this solid one, it's doing a conduction module. So they already have inside these two models and coupling inside. Just in case, you say for the solid mechanics, no, right now, because for what we're doing, we're just sputtering and we are observing that there is no effect of one layer over the other. For a more advanced module, we understand that one of the layers produce an external strain, an internal strain on the other one, and that's where we include that that additional layer. But I decided not to include it here just for simplicity on this model. So the answer will be yes, but based on specific cases, not in general. Okay, and right now we are just assuming that they are just perfectly coupled. Okay, it's very important that you define a good mesh. Sorry, give me 1 second. So I wrote something. That you define a good mesh. Most of the problems that we are gonna have, it's with the meshing. And right now, this model is very forgiving, and we can have a coarse mesh. I'm not gonna talk about that one. If you have some special needs for the mesh, please let me know and I can help you designing the best mesh for that one. One important problem that you can try to solve is try a very simple model and generate, for example, a volume metric, for example, temperature and the maximum temperature, and run it with a very coarse mesh. Then refine the mesh and run it again. Refine the mesh more and run it again. And try to track the temperature for different meshes. There is a point where the model just stabilizes with the number of mesh items, this number of domains that you can see here. Generally speaking, 100,000, less than 100,000, it works good. But it depends on your specific physics and your specific geometry. If we're gonna do, for example, an analysis through the thickness of this layer, look, we only have 2 triangles here. So it means that we only have 2 data points here, and that's extremely low. So if that's the case, we will need to include and refine the mesh on this one. But for this model, we don't need, that's good enough. So it depends on your specific attributes and your specific problem. Now, the most important part is now we're gonna simulate. And for the simulation, we just need to add the studies. So the first study that I'm gonna add, and I'm gonna study group, is gonna be the easiest one, and is the stationary. If, and this is a big if your model is very well constrained, very well defined, this stationary should run very fast. It should take like less than a minute, less than 2 minutes, and everything goes smoothly, and you will have a nice solution. Okay, this is the first test that you need to do. If something just pops up, it's because you are missing some of the variables or some of the nodes. You forget to make a click on one specific boundary condition. So look, COMSOL is not taking very long, and it's giving me a result for this type of model. So it's very important that you have this simple test that prove that whatever you have, it's good. It's part of the validation. You need to do this validation. You need to do experiments, not only experiments in the lab, but experiments here that gives you confidence that the results are correct. For example, if you're dealing with currents, just verify that the current multiplied by the resistance is equal to the voltage in all the points. Otherwise, you're having a trouble at some point, and some material hasn't been well defined. I mean, those little verification points will save you a lot of time and a lot of problems. And that's what is gonna take long. Look, be confident on your model, but also be very patient. Generally speaking, it takes me between 20 and 50 different simulations to finalize a model. This is not that I have one file and that's the same file that I used the first day and I'm gonna use it at the end of the publication. No, I usually try to fabricate like between 20 and 50 different models and 50 different versions until I get exactly what I want. Once I want it, I just rinse and repeat and run over and over. So what I'm gonna do here is automatically it's gonna generate the stress, the temperature, but look, it's generating the temperature for the whole air. And I don't want the temperature for the whole air. So there is a little trick to remove the air again here. And is in the data set, I now have the study and I can add a selection in the study. And in that selection, I can select the domains. And I can say like, oh, I only want results for the beam. I don't want the air. And in the same reason, I can use this one, the click and hide my air. When I do this, the rest of the simulations are only gonna see the beam. And that's the biggest advantage. So that's exactly what you should do to try to simplify your solutions. The other thing is, that's the easy one. This is only one current, 50 milliamps, and I can have like the isothermal plots. Right now, I don't want the isothermal to be in T. I want to be in degrees C. That's very easy to change. And now I change it in Celsius, and I have the electric potential. I don't like these bars, these simulations, so it's personally, instead of a multi-slice, I try to hide this one. I'm gonna disable this one, and I'm gonna use just a surface. And instead of the solid displacement, I'll do electric currents, electric, and the electric potential. So now I have a surface of the voltage in, or perhaps millivolts. Look, it's millivolts and the current. But this is not enough. I mean, I need more information. So the next study that I'm gonna add, it's going to be the parametric sweep. What is the parametric sweep? Now that I define a variable here, a parameter that is current, I wanna know for different currents, for example, from 0 to 180 milliamps, what is going to be this deflection? Because so far, I just find one deflection and one stress, and it gives me only 1 point. But I want to know a little bit more. So I'm going to add the parametric sweep. And in this parametric sweep inside the study one, I'm going to add the current. And I'm going to add a range starting from 0 in steps of 1, and it's going to stop at 80 milliamps. And of course, it's not milliamps, so it's milliamps. And then I'm going to run the study. I'm going to compute this part. I already know that this takes a little while. So let me bring the solution already for this one. Because look, the stationary takes like 30 seconds. But if I'm going to run 20 of those, it's going to be 30 seconds multiplied by 20. So it's going to start increasing the time. So I already solved all the problem, all the times for this model and did all the solutions. What I'm going to create is just nice plots. So let me save this. I don't want to damage. And what I'm going to do on this model is I'm gonna remove this one. As I mentioned to you, I already run the simulation, but I'm gonna do this test with you. It's like the cooking show. You already have the turkey already finished. Sorry, give me 1 second. Okay. So here, what I'm gonna do, don't pay attention to that crazy one. We have the same stress, but when I finish running the parametric sweep, now I'm gonna have multiple values of current from 1 to 18, okay? And at different currents, I'm gonna have different behavior. So what is the behavior that I'm gonna analyze? So first of all, I wanna know the temperature. What is the temperature at the different currents? So I'm gonna create, let me remove this. I'm gonna add here in derivative values, I'm gonna add a maximum. And this maximum, it's a volume maximum. And this volume maximum is for the two volumes wherever we have the, it's wherever we have, I'm gonna remove this one for clarity. Wherever we have the beam, wherever we have the beam. And I'm gonna evaluate the maximum temperature in degrees C. And I'm going to hit evaluate this one. And now that we evaluate, we are gonna create a nice table that is gonna be here. It's going to be table 3. Let me delete these ones. It was from the, sorry, it was from the previous model that I run. But this value, I'm gonna evaluate again, and immediately as I evaluate, it pops up a table here that is table 1. What I'm gonna do is gonna right click a 1D plot, and in this 1D plot, I'm gonna add a table graph. And the table that I'm gonna use is, of course, the table 1. And I'm gonna say plot. So right now, I have my input as current from 0 to 120, and is running the temperature between 20 and 380 Celsius. And that's exactly what we wanted for this model, is what is the temperature? Now, after knowing at different currents, different temperatures, the next question is, okay, how much is the deflection? So I can go ahead and right click. I'm gonna add a 1D plot. And at this point, I'm not gonna generate a table because I'm gonna do a measurement of a single point. And the single point is gonna be this little fella here. What is the deflection? And is the deflection in which axis? So I'm gonna change here to replace the expression. And I'm gonna say, okay, well, please tell me in the solid mechanics, what is the displacement? What is the displacement field, and what is W? W is the displacement field for Z, the Z component. So if you remember here, when we start defining this, right at the beginning, I said like the displacement here is my delta W, That's exactly this W that we are managing here, we're using here. And if I hit plot, this is telling me, okay, perfect. Look, for my different currents in milliamps, 2, 4, 5, and if you want to change the milliamps, you just go label in and just say the units, milliamp. And now we have the milliamps here. For different currents, I'm having a displacement of -1, -2, -3, and the maximum displacement is going to be -3.8 milliamps. Sorry, -3.8 micrometers for 18 milliamps. So now we understand what is the temperature. Look, the temperature, and I can rename this. This is going to be temperature versus current. And this one, I can rename it, and this is going to be displacement versus current. And the last one that I'm going to generate is, I'm going to duplicate the strain. I'm going to try to evaluate the three things: the temperature, the stress or the strain, and I'm going to try to evaluate the what is the current and the displacement. That's what we need. So I have from the stress, the stress solid, that usually the von Mises simulation that COMSOL gives you. I'm gonna duplicate this one. I'm gonna do a little modification on this one. I'm gonna call it like the strain of the material as the original, the strain tree. I already did other strains. And what I'm gonna do is, look, you are doing a surface from the parent, and instead of the von Mises, I'm gonna use a different method. And this method is gonna be just to calculate what is the strain, but it's not gonna be a numerical approach. I'm not interested in the number. I'm just, I'm interested in just an approximation of what is happening with the stress. With the strain, sorry. Ultimate, I wanna know where do we have tension and where do we have compression. So I'm going here in the solid mechanics, and I'm gonna do the strain, and I'm gonna do it's called elastic strain tensor, and it's gonna be the 2-2. And if let me verify quickly that I have the elastic strain tensor, EEL22, yeah, okay. So in my elastic strain tensor, now I can see the strain, the material. Again, this is a qualitative approach. And in this qualitative approach, I'm not very concerned about the numbers of the units. It's just the model in Y, the 2-2 is the Y tensor, the Y component of in the Y direction for the tensor of the strain. And I wanna see in a different way. I'm gonna say, instead of rainbow, show me the wave, because the wave showed me positive red and negative blue. And I'm gonna say like symmetries with the color range. So it's gonna be positive and negative. Right now, it's gonna be the same value, -20 for negative and +20 times to the -3 for positive. So what I have now, and I'm gonna use this one, is for the different currents, I have an indication, or where do we have a strain, because I have tension, is the red are tension, and the blue is compression. And look, for the two films is very different. So it's giving me a graphical representation of what is happening on the field. I have the tension on the polymer at this point, and this polymer here is under compression. And using this information, I can go, and because I did a parametric test, I can go nice and use the player to have a very nice simulation or video of at least 25 frames, wherever at different currents, what is happening with the beam, and how if I play it again, how my strain is happening at the different currents. So just to summarize and to open the floor for some questions, we use the Joule heating approach that COMSOL has inside to couple the solid mechanics, the heat transfer, the electric currents into a Joule heating actuator that we are passing currents, and we are passing currents to heat up this conductor, and we are gonna deform the passive layer, and it's gonna start bending that. And with that, we can understand what is the temperature versus the current, then what is the displacement versus the current, and at the end is how my beam is behaving, where do I have tension and where do I have compression. And that's exactly what the goal of this tutorial. So thank you very much, and feel free to ask some questions. The models are going to be available later tonight at this website. I'm going to send it to Kartik, and he can publish and download it and put it on the perhaps on the Wikipedia or in the server. Any questions?
I have a few questions, but I'll wait for others to ask if they have any questions first. Okay, I'll ask a question now. So, just out of curiosity, like usually we also try to do things such as, you know, how like make a symmetry in the object so that we can reduce amount of like make the processing faster. Did you think about like using a symmetry in this device which you made?
Yes, definitely. The problem with the symmetry is that we observe that the current distribution is not at this scale, 100 microns and 50. The current distribution is not completely uniform, and therefore the temperature distribution is also not very uniform. So it damages a little bit the symmetry, and when we want to make this a little bigger and start including like more of these fingers, this is a single finger for the actuator. When we start having multiple fingers, for example, 4 of these actuators, these 2 are going to heat up more than these 2. So trying to do the symmetry on only one is not giving us all the information that we want on the model. This is kind of the simplified version that we could obtain. But yes, you are right. Please always try the simplest thing. Start doing things in 2D, jump into axisymmetric if you can, and then as a last resource, move to 3D. The more simple the problem, and a problem that you can calculate by hand and corroborate by hand, it's ideal. That's the type of validation that is going to be very useful for everybody.
Okay, and that makes sense. I had another question. This is something which I'm facing with my with my simulations right now. I'm having a trouble to understand. So you discussed parametric sweep, right? Have you tried to look at function sweep?
I tried it in the past.
Okay.
And it worked,
okay.
But I don't. I didn't pursue it further than that. I know that it worked. The only problem is the function cannot be so open. So perhaps what it worked for me in the past, it was breaking the function into little segments, because most of, I mean, for example, here your model, let's see, the model here is non-linear. So perhaps if you make a simulation for the function from this point to this point, and another simulation from this point to this point, and another from this point to this point, it will work better than trying to simulate the whole behavior of the machine.
Yeah.
So it's more like in the electrical engineer mindset. Try to define regions of linearity or regions of quadratic function, and try to use those. Very complicated functions, COMSOL tends to get lost on that one. And a simple thing that you can use is run the model without running any specific physics. So for example, run the easy one, the DC, for example, this one. Run AC/DC with a variable called temperature, and temperature is a quadratic function of the pressure, for example. I don't know. I'm just making up things. So running the electrical current, such as you're going to have a solution of that specific variable, even if you are not using that variable there. And you will have an evaluation of what is the variable doing at different temperatures without damaging the model. Once you verify that your model is accepting that inner variable, you can do it. One way that we tried to use it, for example, in the past was try to use it in the magnetic materials. But we observed that instead of doing a simulation parametric with a function, it was better just to define here in global definitions. Sorry, no, not here, in component, to define, sorry, here, inside the component and definitions, to define a function here. So do not run the study based on that function, run the study based on a parametric value, but compute the function value. So for example, a function x squared of something, just create the function x squared, but do not try to run parametric to the function, but run to to parametric to x, and calculate all the time x squared. That seems to work a little faster for COMSOL.
Okay. Yeah, I'm having some issues with my own simulation now. So yeah, this is helpful.
We can see it offline if you want.
Yeah, sure. But anybody else, do you have any questions? Come on, this is one of your few chances which you get to ask like tons of questions of COMSOL.
And it's very, the last piece of advice is go and use the other sources of documentation, are very powerful, and use examples that are already there, and use the webinars that COMSOL offer. Please, everybody that is working with COMSOL needs to register to the COMSOL website. Your group, IMG, is paying a lot of money for the license, such as everybody can just send an email and ask some questions. Of course, the better that you understand your model, the better the answer that you're going to receive. I see that we have some questions from Lyden.
Yeah, I really like the talk. That was excellent. Can you share your email? Actually, I want to talk to you about this 2-photon polymerization.
Here is my information. It's cvelescu@andrew.cmu.edu. I'm going to send it today to Kartik, this information, but you can copy and make a print screen of this.
Okay. Oh, yeah, print screen.
Yeah, please feel free to contact me if you have any trouble with the simulation. I perhaps can have solved a similar problem, or I can point you in the right direction doing that. And COMSOL during this quarantine is doing some very interesting workshops and seminars. This week, for example, they started a workshop series, and they are doing magnetic coils or AC/DC for coils and magnetic applications. Very interesting. 1 week of only AC/DC for magnets. They're gonna bring several workshops and tutorials in the upcoming weeks. So please join the website, put your email there, and you will start receiving the information. You will find something very interesting, and especially COMSOL that every year change one version of the software. It's adding more functionalities. I remember just a quick anecdote. By the end of my PhD, COMSOL finally released the variation on the magnetic modules that make sense all my simulations from the last 5 years ago. I was doing it manually by COMSOL like the last year, like 3 months before graduating. He just released and updated and say like, oh, look, everything that you did with so much pain, here is in a new update. It was kind of nice. So please be conscious that this is a software that is evolving with the researchers. And so it's very cool to receive the most updated information.
I want to ask another question, Camilo. So
yes,
for like you did a stationary sweep, right? For time-dependent sweeps. One of the issues which I'm facing with my simulations now is when I'm trying to do a time-dependent sweep, I also want to change a variable, which changes with the time, right? So for example, when we set parameters in the parameters one thing in the global definitions, those parameters stay fixed, right? But if I want to change a variable which changes with the time, how would I be able to do that?
That's a very good question. You try to avoid like a parametric sweep inside another parametric sweep, or a time-dependent sweep inside a parametric sweep, because for COMSOL it's kind of a nightmare, and the amount of data that you are generating it's increasingly it's a lot. What you can do is just, instead of defining, I mean, if your model is time-dependent, define a time-dependent study, and inside the time-dependent, just have an extra function here. So you, for example, here you can do a function or an interpolation function, wherever you said like, oh, this function is sin of the time. Okay, and the name of this function is XYZ, I don't know, XYZ. Okay, so you create a function that it's somehow related with the time. You define this function and it's related with the time. And when you insert it here in the time simulation, instead of trying to force all the solutions to that, it's just solving the simple interpolation here, and it's way faster. And COMSOL is doing it considerably more easier than just having a parametric inside a time dependent.
Okay, so if we have to call that interpolation int1, I would just like run it normally, right? I wouldn't have to call it specifically.
No, you don't need to call it. It's already solving it. Okay, so if you run it at different times, it's going to run this simulation multiple times, and it's a an independent solution there, and it's very fast for COMSOL. It's simple. And the other thing that you can do is, look, you don't need to have everything in the same study. You can run a portion of the study, make another study with a different condition, and run it again after the second study, and so on, so on, so on. So if you finish one portion of the study, you can save, and you already have that data. And then you move to another study and generate more data. And if something crashed in between, you already saved most of the information.
Okay. This is quite useful. I didn't know about like running them separately. I mean, this quarantine time only has made me do like a lot of simulations. I was doing experiments only earlier, but this is nice time to do simulations.
Yeah, it is a nice time. Please take advantage of this, and this is fun because remember, this is research, and this also it's an experiment. You just need to be more careful with the experiment, because you're gonna start spitting data like crazy. Can you trust on your data? Well, make sure that the results are accurate. Well, how? Make a small test. Make little experiments that prove you right or proves you wrong. Use the same method that you're using in your lab here. And you will see that you're gonna generate a lot of information, but you're combining it very nicely and very fast. It's a very powerful tool. I definitely love it. Love it.
Anybody else? Do you have any questions for Camilo, so that we don't take much of his time? I think it's already 10 minutes more than what we wanted. But if anybody else has questions, please ask now.
Please don't hesitate in contact me. And well, it definitely was a pleasure. Please call me or send me an email, and I'll be available to solve any question that you have. Thank you very much for inviting me.
Thanks a lot, Camilo. You're really helpful. Thank you.
I hope so. Bye. Stay safe, please.
Thank you.